and we, along with my friends here, are here to talk about IP traffic management applications. We were in Miami. I think I recognize some faces from Miami, and we talked about a lot of technical detail about how to collect and scenarios on collecting data to do interdomain traffic engineering. And some of the feedback we got from that was that, gosh, some real case studies would be a whole lot, would sort of be valuable in doing this. So what we tried to do this time was expand the scope a little bit to go from just technical detail about how to measure stuff into, what are some of the problem statements and what are some of the applications you can do with this stuff, and then actually show some examples about how people are using this sort of technology to answer questions. So, given all that, I titled this IP Traffic Management Applications, Measurement Analysis and Optimization. Who we are, again, my name is Josh Wetman, I work for Ixia. We have Andrew Lang from Exodus and/or Cable and Wireless. Matt Meyer from Global Crossing, and Joe Abley from MFN, in height order ranking. So when we were in Miami sometime back, I guess that was February, we defined a process for solving problems using this sort of technology. And it started with defining goals, clearly defining a problem statement so that as you went to measure data, you knew what you were doing, how to group it, and how to look at it. So defining a goal, defining a problem statement, selecting a measurement scheme, and then going forward and measuring in your network the right data points and the right data objects, analyzing your data in a sane fashion, and then refining your goals based on your analysis and taking some action to solve your original problem statement, and then go to one and start again. And that was applied specifically to interdomain traffic engineering back in Miami. So I personally learned a few things from the Miami presentation. One is that more detail on problem statements and measurement schemes seemed to be what people wanted to hear more about. Some real examples and case studies of applied solutions would be helpful, and that sometimes I start to talk really fast and that I should talk more slowly. So feel free to remind me if I forget to do that again. So, what am I talking about? The goal here is to talk about a broader set of applications that exist for routing and flow data correlation. There's darn near an infinite number of things you can do with that data set, and yet remarkably few people use it. So, defining some problem statements and defining some scope of measurement seems like it would be a way to help people get into doing this stuff. So, very specifically, I wanted to focus on what are the problem statements, what are the business-related problems we're trying to solve, and then what are the measurement issues and the scale issues in designing solutions to those problems. Is that loud enough yet? Okay. So I really wanted to focus on those first two things because that seems to be where most of the questions came from. So when we talk about problem statements and solutions, solutions have a few things that they need to do. They need to solve real business problems. We all sort of live in an economic environment now where solving problems that aren't really economically based, kind of take a back seat. So the problems we're solving have to sort of, cut costs or drive revenue. I'm an engineer at heart, but I can be an engineer all day and not end up working for a company at the end of it. So there's just some sort of bottom line economics here. And one thing that I see a lot happening, or some things that I see happening a lot, is that a lot of the solutions that are proposed to problems, the solutions are more expensive than the problem is. And that's something that I ran into as an engineer a lot, is that I identified a problem, I would identify a solution, and it turned out that when it comes right down to cost, the solution was far more expensive than the problem. Finding economically sane solutions to problems is just a major thing these days. And then, finally, it needs to provide relevant engineering data. It has to be problem statement relevant, and, it's really easy to go overboard and try and collect everything underneath the sun, and you end up collecting so much data that you run out of disk, run out of memory, you need too many boxes, and it becomes too expensive way too fast. So the goal of what I'm doing here, at least what I see it as, is that by the time I'm done talking about this stuff, as Andrew and Matt and Joe get up to do their case studies, you should have enough information fresh in your mind to apply whatever your problem statements are and whatever your network design is. You should be able to apply what you have locally to what they're talking about, such that that's helpful for you. Hopefully that's what happens. So I came up with a list of applications that I thought would be interesting to talk about in terms of business problems to solve. The first one being interdomain peering optimization. I mean, everyone here needs to expand or contract their peering in some capacity, or at least make it work to the best of your ability. Interdomain congestion management. People have packet loss between networks. How do you solve that problem? Customer acquisition. That seems to be something that people don't talk a lot about. I won't talk forever about it. But network policy enforcement, intradomain traffic engineering, and there's a list of others that we'll touch on briefly. The reason we didn't call this interdomain traffic engineering and interdomain applications is that, there are some pretty interesting uses of this stuff within your own network, as Andrew will talk about. So we sort of broadened the scope, I guess is the right word. There is a microphone right behind the projector here. If anyone has questions, please ask whenever you feel the urge. This is sort of for your benefit, so please stop and ask if you have any questions. So again, every application follows the same model. You define a goal, you measure appropriate data, you analyze it, you refine your goals, and you take action. And the focus of what I want to talk about on is defining your goals and then your measurement scheme. And specifically for your measurement scheme, what is your network scenario, or what is a network scenario to consider? What is the deployment scenario for that network design? And then what are the implications of your deployment scenario on your network scenario? And what I get asked most often is, how much disk do I need? How much memory do I need? How many collectors do I need? What are the hardware requirements? What are the hard numbers I need to know? And the answer is always the same. It just depends on a ton of things. And some of the things are quantifiable, some of them are not. And all of them will depend on what your network looks like. So my goal is to help you figure out those answers for yourself, because, I will never know the answers, and no one you ask outside of your network will ever know the real answers. There is what I think to be a pretty good repository of more collection-specific technical detail in our Miami presentation, which is online. If you're looking for configuration, more stuff like that, take a look at that. I'm fine with being offline. It's at that URL. Please take a look if you have any questions. Joe or I, who did that presentation, happy to answer them. So the first problem statement that I thought we'd talk about is interdomain peering optimization. The problem statement for that, as I sort of see it, is reduce your interdomain transit costs while increasing quality of connectivity. Clear business win there. You reduce your costs, it's cheaper, you gain finer grain control of your traffic, and while that can increase the complexity, nobody here, complex BGP implementations isn't new to anybody here, I don't think. You end up getting closer to your end consumers in terms of the traffic you're sending across your network, both on-net and off-net, and there's just a clear cost savings. It's an economically sane approach to peering that solves the real problems instead of guessing who, quantifiably who, and you can make decisions based on whether that's economically viable for you or not. For more information, you can see Bill Norton, who's sitting here in the front row, The Art of Peering, and I actually thought this was really funny when I wrote it, Sun Tzu's The Art of War, because peering can be sort of a pain sometimes. A network scenario for peering optimization, I chose a very generic one, a hierarchical network design where you have core transit facilities and your on-net, off-net traffic comes in at some edge box, whether it be a peering router or a gateway router or a web hosting router or whatever it might be. Your peers are not offered transit services, and your primary concern is outbound load. A simple picture of that is here you have some number of transit routers. Each edge router is multi-homed into a set of core routers, and those border routers connect you to other ASs, which then connect you to other ASs. So a deployment scenario for this problem statement, considering that network design, specifically for flow export, is that you would collect flow data on the core access links. All the traffic presented from your core to your edge, ideally should be going off-net to your peers. The sampling granularity can be, moderate, 1 in 50, 1 in 100, 1 in 500. You're doing long-term capacity planning here, so you don't need to catch every spike in every dip in traffic. You need to know long-term trends. Sampling can, depend quite a bit on your platform. A Cisco 7500 currently doesn't do sampling. 12004 series only does sampling on the new line cards. So, you know, you're going to have to mix and match. A Juniper will have different requirements than a Cisco, but you know, moderate sampling granularity much better. You don't have to have one-for-one to do capacity planning. You don't have to have every link or every packet coming across every link. It's just not necessary. What you want to do with sample data is to get real link characteristics, and you extrapolate those based on valid sampling data. Another question I get a lot from a lot of people is, how long do I have to sample data to make it valid? If I'm sampling 1 in 250,000 packets, how long do I have to do that before I have a valid data set? And the answer is never. It will never be valid. If it's invalid when you first collect it off your link, it will never become valid no matter how long you populate a group. There will be a low number of total links exporting flow data in this design. We'll get to that. For BGP, since we're looking at outbound load, iBGP from the edge box is all that's required because iBGP clearly will pass you external active paths. That's all you need for traffic going off of your network. The goal in collecting BGP information for this is to communicate BGP routes that correlate to traffic flows. Specifically here, the destination IP address needs to find a match in BGP in order to generate useful data. Whenever you're doing this sort of thing, whenever you're doing traffic engineering or billing or anything like this, the routing information you collect needs to correlate to the flow information you're collecting. We'll get into that a little bit more in a second. So here's a slightly modified picture from before. As I said, we're collecting flow data from the core access links, you know, inbound on links on the border routers that connect to the transit routers. That allows us to see all outbound traffic without having to collect on some large number of interfaces. And that's what makes this design model really, you know, work well with this sort of problem statement, because you have a low number of links, which means you're putting less load on the router, which means you're, you know, it's a win everywhere. You see all the traffic. And then we're simply doing iBGP from those routers because all we need those routers to do is pass eBGP installed routes to us. So deployment implications for interdomain peering optimization. The number of collection nodes you need, low to moderate, depending on how many peering locations you have. Flow export is obviously UDP based, so you don't want to transit it halfway across the world if you can help it. So if you have lots and lots of peering locations, you might need a few more boxes, but all in all, you're not collecting off a tremendously large number of links, and your BGP is pretty easy in standard iBGP. So the number of boxes you need, pretty low, which means the requirements for those boxes will also be low. Disk usage, metrics for that. I mean, disk usage is pretty low for this. Metrics to think about are time. How long do you want to keep the data? I mean, you know, pretty standard stuff. If you want to keep, you know, 200 years worth of data, you're going to need a lot of disk if you're willing to throw away stuff when it's 30 days old or 90 days old after you've, you know, taken a peering snapshot. You know, the disk requirements go way down. Number of interfaces. The disk usage is generally linear, or number of interfaces is a linear multiplier of load. If you have 10 interfaces, you'll have some amount of disk space usage. If you're collecting all the same data types on all the same interfaces, if you add one more, it will go up by a factor of X. If you add another one, it will go up by a factor of X again. I mean, it's just it just balloons based on the number of interfaces you add. So watch that. Flow diversity. That's possibly the biggest factor in disk usage, especially if you're collecting raw data. It doesn't matter how fast your link is. It only matters how many unique flows are going across in a given period of time. So if you have an OC48 and it's just one huge flow, the number of flow records coming out of that interface are going to be very, very low, so your disk requirements will be very low. If you have a DS3 but tons and tons of microflows, you'll have a lot of flow export data coming off that link. And that's just a really hard question to answer. What's the flow diversity of your link? You know, there's just no way to ask the router that question. And then flow export version, obviously version 5 is going to be a whole lot chattier than version 8. In terms of CPU load, again, it's pretty low. You know, this is a pretty low scale question to answer. Number of interfaces, you know, probably pretty low. Flow diversity, still a hard question to answer. The BGP model, iBGP scales a whole lot better than, you know, N by route reflection, as we'll see in a second. And again, you know, flow export version, handling tons and tons of V5 packets is harder work than tons and tons or fewer V8 packets. I wanted to make one quick note about paths to the source. When you're talking about looking at traffic in the AS path realm, we're usually talking about traffic going from your local domain to the destination. And a lot of people, what they want to do is they want to talk about the paths to the source IP address. They want to know how traffic is arriving into their domain and try and make peering decisions based on how traffic arrives into their network. And that's just a really, really hard question to answer, mostly because when you're mapping routing data to a destination IP address, there is a very strong correlation to the forwarding path. The route that came to you is how your traffic will be delivered, or at least it should be almost all the time, because every router in the path had to install that route as active in order to propagate it along to you. Mapping routing data to the source IP address is a very weak correlation to the forwarding path. You don't know how the source AS sent traffic to you. You only know how you would forward it back to them. And the odds are very good that it's an asymmetric path. So if you were to collect routing data per AS path to the source AS, you would get lots of information, but it would be near impossible to tell you if it was correct or not. But there are some things you can do. It's not just it's not that you just can't do it. Most routes in the internet have a single origin AS, so you can usually say that that's correct. And if you're collecting on a peering link to, say, provider X, and you saw this flow come across that link, you know it came from provider X. So you can make intelligent statements about your neighbor, and you can make intelligent statements about the source. It's just sort of that middle mile that's very tough to do. Make sense? Okay. So problem statement number 2, which is just really close to the first one actually, is interdomain congestion mitigation. Problem statement here is save money by identifying and eliciting control over discrete traffic segments that are causing congestion. My link to provider X is full. I have another link to them, but I need to find some atomic amount of traffic within my congested link to move to my uncongested link. I said here that congestion is usually bad. If I said congestion was always bad, someone would certainly come up with a scenario where it was okay. It's usually bad. It's usually a problem you need to fix. I'm sure there's cases where it's not. Most of the time it's going to cost providers money, whether it comes out of SLA payments, or whether it comes out of lost customers or something like that. The problem here is finding the right size fix in order to consistently and persistently address the problem. I don't want to do this every 2 days. I don't want to have to do this all the time. I want to find what the problem is, and I want to find a persistent fix to my congestion issues. And the return on investment here is very clear: higher quality of service and lower operational costs. So in terms of network and deployment scenarios, it's just very, very similar to peering optimization, except that your time domain is much shorter, whereas in peering optimization, you're looking at 3 months, 6 months, 9 months worth of data as a snapshot. Here, you're looking at days and hours. Over the last 2 days, link X has been very, very congested. I need to do something about that specific spot in my network. And it requires, you're looking at the link level instead of some abstracted domain. How much does my AS send to this AS or that AS? And it requires retention of more detail to answer more specific questions. That has implications for our deployment. So still the number of collection nodes is low. We're sort of collecting on the same links as we were for the peering optimization bit. The disk usage is moderate, and I say it increases here because even though the time with which you're keeping data may decrease, the number of different kinds of traffic or the number of different kinds of data that you might need to keep increases. And so the more tables you collect, the more disk you're going to end up using. And the CPU is generally low. It grows with the number of interfaces, and it grows with the flow diversity, and it grows with, depending on which BGP model you have. But again, doing this is a pretty low resource problem to solve. It's just, it's not that big a deal. So the third one is customer acquisition, and I wasn't entirely certain if I should put this in here, but it comes up a lot, so I thought I'd mention it. The problem statement is, increase revenues by identifying and targeting potential customers based on the current traffic trends on your network. Publicly, very unpopular. No one here is going to nod their head and go, yes, I'm very interested in this. Privately, I know a lot of people who, try and target customers of their competitors. That just happens in every market. When it comes right down to it, is anyone not in need of more consumers in order to offset generally static network costs? You've built this network. You need to find consumers for it. the best consumers you can find are people who already need access to your network, and that's what the flow and routing data gives you, is who's currently the consumers of my network. Getting an ordered list of them and then going out after them. So you increase your revenue and potentially decrease peering traffic. So the network scenario, it works on just about every network. Actually, if you have no customers and no peers, this will not work. But otherwise, it should. There's bound to be at least one network in the world like that. Or on their way. It works in the same hierarchical model that the peering optimization bits do. The flow data is collected inbound on peer links that you want to target for customer acquisition. Say one of your competitors was stealing customers from you. You wanted to sort of return the favor. You would collect flow data inbound on your peering links with them to find an ordered list of consumers of your network resources, and you would likely order those based on the sources of traffic, the sinks of traffic, and ideally to find the people who source and sink the most traffic to your network. And then you send in the jackals, which is my code word for the salespeople. In terms of flow collection inbound on peering links, sampling granularity can be generally coarse. You don't need exact numbers. You're not going to people and every megabit and every kilobit is not important to this question. It's just getting an ordered list of opportunities. So this is a pretty low resource consuming gig for the routers and for the collection scheme. The same data normalization procedure as peering optimization would be used here. For BGP, this is a slightly different model. Since you're looking at traffic mapping onto your network from the edges, this requires BGP route reflection from the exporter or representative router. We'll get to that in a second. The idea here is that if you don't do route reflection from the router that you're collecting flow data from inbound on external links, you're likely mapping traffic onto IBGP learned routes. If you're not doing route reflection, you'll never learn those. You'll only learn the locally externally installed routes. You need route reflection in order to see the IBGP domain and what routes are being mapped onto your network. If you don't do that, the CFlowD concept of bucket zero gets very big, where you collect all this information and it just never matches anything. So you just get this huge bucket of what equates to, I don't know what to do with that data, so I'm lumping it in the default bucket. So the network design for customer acquisition or things like this is that you're collecting inbound on your external links to your peers, and that you're getting a route reflection feed from either your border routers, or if your border routers are already clients of some higher level route reflection scheme, like your transit routers, there's no reason your collector can't simply get the same route reflection feed as your edge routers do. If they're part of the same peer group, they will learn the same routes in the same time. So, it's just an easier way to make this go. Deployment implications for customer acquisition. Collection nodes can, it can increase quite a bit. I mean, you may have quite a bit larger number of external peering links than you do customer or access links from your border routers to your core routers. In terms of disk usage, again, time is an issue here. How long do you want to keep data around? For every day that you want to keep data around, your disk requirements will go up. Interfaces will drive this up, since you have a larger set of interfaces, and interfaces are one of the primary ballooners of disk usage. There's bound to be a better word for that, but I can't think of it at the moment. That will increase disk usage. Again, flow diversity and the traffic types you want to keep, but this is generally an AS question, so there's just not a lot of traffic types. And then CPU, again, it's sort of moderate. You have a larger set of interfaces, and the scaling factor of route reflection, it does not scale as well as anyone who has routers knows. You just can't terminate as many route reflection feeds as you can IBGP feeds, because you hear that many more paths from every router, especially at initial session synchronization. I think it's very bad. Any questions while I take a sip of water? One more chance? Okay, so the next problem statement, and sort of the next economics-based problem I wanted to talk about, is network policy enforcement. There's a lot of different words for that, but the bottom line is that as a problem statement, I want to reduce my operations costs and my outage times by identifying routing and flow issues proactively. I want to, catch things before they become major problems. And more than anything else, when I do see major problems that I couldn't have caught ahead of time, I want to solve them the first time they happen, not the nth time they happen. When you see a malformed AS packet come into your network, you see something bad happen, you don't know what happened, you have to formulate a theory and then wait for it to happen again to see if you were right or not. If you were lucky enough to be right the second time, then you see it. If you weren't lucky enough to be right the second time, you have to go through that iteration again. In doing things like network policy enforcement, you have a record of all that. You simply keep asking the question until you get it right. So details of this, identify traffic that shouldn't be on your network. Are peers dumping traffic at you? Are they sending routes, or are they sending traffic to you for routes you didn't announce to them, which is not hard to do. Are your mostly intra-Europe customers actually sending most of their traffic to the U.S. over those expensive STM16s? Is traffic doing what you think it should be doing on your network? And if not, it's just a really great thing to go find that out, because you can take some recourse or possibly derive more money from it. And then in the BGP domain, is peer A propagating routes from peer B? Did one of my customers send me their other provider's routes by accident? Am I getting default from the wrong place, or if you're a default-free network, from any place? Sort of catching those snakes in the grass before they bite you. The network scenario, again, some large-scale IBGP deployment, some complex network policy. If you only have one provider of BGP routes to you, there's just not a lot of enforcement to do. Multiple exit points for routes. You likely are peering with people at multiple locations, and you have both transit and non-transit relationships with your eBGP neighbors, and very likely in doing this you'll have different questions, and that you'll need to collect flow inbound and perhaps outbound on links and on routers. That's a good slide. So network policy enforcement, BGP deployment scenario. A full mesh IBGP collection allows you to evaluate all of the candidate routes that your IBGP sees, as well as all the active routes. So doing a full mesh gets you a whole lot more information than simply doing one route reflection feed from a router. You get to see everything that all of your IBGP sees, and that allows you to see a whole lot more causality. There's got to be a way to turn that off. That allows you to see a whole lot more causality than simply getting one route reflection feed and sort of evaluating what the effect of what your IBGP did. Ideally, it would just be really great if we could evaluate all of the routes we hear at all routers instead of all the routes that we hear on all routers that were selected as active. So ideally, it would just be really great if you could evaluate every single route that came into your domain from every edge. That way, you can catch candidate routes that aren't selected at some edge router, but that do represent a problem, such that if they ever did get installed, you might face an outage. So that doesn't currently exist in BGP. Another question that I get a lot from people is, well, Juniper has this thing called advertise inactive, and that's how I would get all that information. That's not actually what that command does, even though the documentation seems to tell you that's what it does. There's just no facility in BGP for me as a neighbor to announce you some route with some NLRI and then send you that same NLRI again as an atomically different unit. It would be an implicit replacement. There's just no way in BGP to currently do that. But luckily, the IETF is, moving very slowly at solving this problem. And there are two internet drafts that are out there for you to peruse if you're interested. One by Walton at Cisco, and one by Joe Abley, who's sitting at the table to my right. Both of which I think would help us do this and would give us a whole lot more visibility and allow us to evaluate and protect ourselves from bad things happening a lot better. At any rate, in the BGP domain, network policy enforcement, you would go out and you would evaluate every route transaction in real time to evaluate if good things or bad things are happening. I just don't know if a lot of people that are doing this right now, but I think everyone should. There's just a lot of value in catching things going wrong before they become huge problems. And I don't know anyone who hasn't had a major BGP catastrophe at some point in the last 18 months or so, or at least the last couple of years. And in order to say what's good and what's bad and what's coming in, there's a general requirement that you be able to define what's good and bad in your BGP implementation, i.e. policy definition. This is good, this is bad. I should hear default from them, I should not hear default from them. I should never hear 701 routes from 1239, et cetera, et cetera, et cetera. Or if that's your relationship with them. So network policy enforcement deployment scenario for flow data. You would collect flow data at the network ingresses and trouble spots. You know, you're going to apply this to potential problems that you're having and go after. You know, should interface X send traffic flow Y? Should my non-transit peer X be sending traffic to any of my other non-transit peers? If you notice them doing that, that's probably a bad thing. Are peers sending traffic for routes that you didn't announce? Here, this is actually a slightly different problem. The sampling granularity can be very, very low on this because you're not really quantifying these things. You're just looking for a yes, no. You know, you're asking a binary question, is this happening or is this not happening? I don't really care how much it's happening. If my neighbor is cheating me, I don't need to know the magnitude of it. I simply need to determine that it's happening or not. And for a lot of the stuff, V5 is preferable because you get all of the raw flow data, which means you can ask a lot more questions. If you're using V8 or the forthcoming V9, you can ask a lot less questions because you're only getting the summary tables. So the deployment implications for network policy enforcement, and I'm thinking of this on a large scale. You know, the collection nodes becomes moderate to high because you're collecting off a lot of interfaces. You're collecting a lot of BGP sessions. The disk usage is pretty high because you're saving raw flow data instead of the summary tables. Again, you know, how long do you keep that data is a major issue in disk usage as it is storage. The flow version I've mentioned a couple times. This is probably common knowledge to most people, but for those who isn't, version 5 sends all the raw flow records out to you. Version 8 does the on-the-box aggregation into summary tables. But there's a resource trade-off there. Version 8 is a whole lot more router-intensive in order to do all that work, but it offloads the collector side and it offloads the network transit load. But version 5 is a lot less work on the routers, but there's a lot more collection side load and there's a lot more you know, traffic on your backbone. So, you know, things to keep in mind. Number of interfaces, again, the number of nodes, the number of links, and the traffic types, including the raw traffic. If you're keeping raw flow data, that is by far the biggest disk consumer of all. So just keep that in mind. And then for CPU, there's a pretty high CPU load for this in terms of collectors because you're evaluating everything that comes through in real time to say is this good or bad. So, you know, this certainly becomes a higher end, more complex series of things to do. Okay, so I think the last one I did is intra-domain traffic engineering, which is obviously, you know, slightly different than the rest of the ones we covered. Problem statement is maximize traffic mapping onto existing internal capacity without using all sorts of expensive MPLS technology. For those of you who have moved to MPLS, it's not the easiest thing in the world to do, and sometimes it's kind of expensive to do. And doing this sort of thing is able to address a lot of the same issues that people use MPLS to do, but without having to do that. Now, I want to say this right up front, MPLS is just a fine and dandy technology. It's not a replacement. It was simply an alternative, and we just don't have time to have the never-ending, is MPLS a good or bad thing debate, to which I can not argue either side. So the network scenario for this, you know, some arbitrary set of IGP links, you know, BGP selects the exit point for your network. It works in any conventional network paradigm where IGPs carry intra-domain traffic to the BGP next hop exit point. If your network is not designed like this, this will not work so well because it's based on the notion of deriving load per BGP next hop from a given source. So most networks I've seen run like this. There are some that do not. For those that do not, you know, have that MPLS. So intra-domain traffic engineering deployment scenario for flow. You're going to collect flow data from the edge ingress links of substance. You know, you don't have to collect data on every single interface all over your network. That makes the scale go through the roof, and it, you know, again, it becomes a solution which is more expensive than the problem. So don't sweat the small stuff. And just like in that hierarchical network model we looked at, you may have, you know, thousands of customer links on a given router, but you may only have 2 links into the core. Collecting on those 2 aggregation links makes it a whole lot easier than measuring every single edge link. And since your concern here is traffic mapping onto your network, not necessarily the actual source interface, you can scale a lot better by doing that. Again, the sampling rate here can be moderate. This is not billing. You're not looking for how many Microsoft Word attachments your customer sent today. You're just looking for long-term capacity planning. And the same concepts of data normalization apply. Sampling normalization is important here because you're looking to put together future plans for your network. You're going to want real numbers for that. So it's pretty important that your sampling be valid as well as, or that your sampling rate be a valid representation of your real traffic. For BGP, again, in this scenario, you're looking at traffic that's mapping onto your network. Whenever you're doing that, you're likely following an IBGP learned route, which means route reflection is the only way to see that information from the edge. And the deployment implications for this, the number of nodes, high. You've got lots and lots and lots of edge routers, especially if you have a very large network that isn't very centralized. Disk usage is moderate. You're using tabular data here. You're not using the raw data, so your disk isn't going to go through the roof too fast. Disk usage will balloon with in proportion to the number of links, the same as the other ones. And aggregate at the edges where possible. You don't want to aggregate you don't want to collect on every single edge link. If you can find aggregation points, one step in on your network to collect that. CPU, since you're doing long-term trending, that reduces real-time CPU load, so CPU load is not terribly high. Again, route reflection does not scale quite as well as IBGP because you hear multiple copies of every path. Other applications that people use a lot with this sort of information is usage-based billing, billing verification. An example of billing verification might be, I have a European customer who we bill because they tell us that they keep 90% of their traffic in Europe and only 10% goes to the U.S. Well, the only real cost I have there is those, across the pond links. Can I verify that this customer is truly behaving that way? And if they're not, I need to bill them in a different manner. DDoS and security applications, am I being attacked? Who is it? How do I stop it? And per-service network design, which is something we've heard a lot of people talk to us about, which is, I've got this pretty big network and I need to continue refining it, I need to continue building it, but I really only want to do that for services that are high revenue to me. I don't want to continue building out my network for plain old vanilla IP service when I make the most money off of real-time voice or video. I want to build out my network and I want to build out my inter-domain relationships based on these services, the specific services that make us money, not necessarily on the entire bulk of our traffic. Things flow export and routing do not do. It does not print money. It will not correct accounting practices. It does not speak in the sort of cool HAL 9000 voice from 2001: A Space Odyssey. It does not make a decent omelet, despite what you may have heard. I thought those were funny. So basically, in summary, there's just a truckload of applications that can help you save money and make money by collecting data that exists on your network, both flow and routing data, and active measurement, though that we didn't cover it here. And that, there's just all sorts of stuff people can do with that. And in almost every scenario, there's a way to install a solution that is far cheaper than the problem that will help you cut costs or drive revenue. And while that's not a very engineering thing to say, I think it affects everybody here. Most everything works on very standard network designs, and the disk and CPU loads vary pretty significantly based on scale, application, and problem statement. Again, I tried to put together general rules for what to expect in terms of what problem statement you're trying to apply, but it will always depend on a number of factors. My name's Josh. I'm from Ixia. Thank you. Questions, Josh?
The mic is behind
It's behind the projector. I'd like to recognize Bill Norton.
One of the things I always hear about is I can either count my packets or I can forward my packets. And I was wondering if you have any anecdotal evidence or stories about where that point is where you don't seem to have quite as much of an effect, or where you see the routers kind of falling over.
Right. The standard vendor answer to I want better accounting on my routers is, well, we can give you better accounting, but it'll be at the cost of better performance. And routers route and forward bits first and foremost. So that not being a router vendor, it's easy for me to say that that's an easy answer for them. I know firsthand that router vendors are working very hard on finding ways to improve accounting. In terms of, sampling on routers for NetFlow didn't always exist. Once we got to higher speed interfaces, on an OC48 link doing one-for-one packet analysis, that's just a lot of CPU work no matter what kind of ASICs you have installed. So that just doesn't generally work. And the goal here is to make the least intrusive network accounting you can without, so that you don't affect performance. So the question I get a lot is, well, what's a valid sampling rate? What N can I install for 1 in N such that when I extrapolate out the numbers, it represents 1 in N? What's a chi-squared analysis? What's a statistically valid sampling rate? And I will give you a very easy answer. I don't know. The problem is that the last study that was done on this in terms of packet sampling was done by KC, who's in the back of the room doing other work. That was done in 1995, 1993, something like that, before there was even a preponderance of World Wide Web traffic on the internet. So traffic characteristics have just changed so much that nobody really knows the right answer. For a given backbone link, or for a given peering link, or for a customer access link, what is a valid N for 1 in N such that I have statistically valid data? So that's the statistician's answer. I can't give you the right answer. Based on my experience in working with a lot of people, seemingly somewhere around 1 in 50 or 1 in 100 on a Cisco GSR or a Juniper router gives you seemingly statistically valid data, and I've yet to see a router choke on that. That doesn't mean it won't happen, but I've had really, really good success with the 1 in 100 ballpark as a sampling rate. That seems to be statistically valid. It seems to not impact router performance, and that is the two goals that everyone seems to have. What is the best rate I can get without impacting the core router performance?
I asked the same question of the Cisco guys, and apparently there are some cards that have some built-in processing that can cost a little bit more money, but have this sort of fix into it.
All right. The Cisco 12000 series router and the 124 series router specifically, just between the chassis and the fabrics and the line cards and the IOSs and getting the thing that you actually want, I find sort of difficult, but you can do it. And so GSRs have the Engine 0 cards, the Engine 1 cards, the Engine 2 cards, the Engine 3 cards, the Engine 4, Engine 4 Plus, and Engine 5 cards. And it's just a lot of them. And every single revision of card does NetFlow in some slightly different fashion. We have customers and we have cohorts that have all manner of cards. They have Engine 0, 1, 2. I actually don't know that any. Actually, I just don't know what the entire composition is, but it's the whole gamut. I mean, they have all of them, and you don't apply a sampling rate per card. You apply it per chassis. So the 1 in 100 value seems to work just fine on a box that has Engine 0, Engine 2, Engine 3 cards as a distribution. I am told, you can't trust me on this, you'll have to ask your Cisco reps, but I am told that the Engine 4 Plus cards, the Quad OC48 and the 192 cards actually have additional ASICs for handling NetFlow that will tolerate a much higher sampling rate. So, your answers will vary, but, I don't know, does that answer your question?
That's the only question.
Yeah. Other questions? Okay, thank you.
We do weddings and bar mitzvahs.
Exodus, a cable and wireless service. I don't come up with these names. I just put them on the slides when they tell me to. All right, what I'm going to talk about today is using some of the flow data that Josh had talked about earlier to apply it to your IGP metrics in an attempt to make them more optimal. Who I am, the information's up there, the emails are up there. I'm living proof that you can in fact survive Chapter 11 bankruptcy, and in this particular case, the ended up in Britain is metaphoric, where it got, of course, bought by the British company, and I'm still in California. What this is this is intended to be an introduction to using the flow information to tune your network. This is not an end-all be-all guide. It's a very, very big topic. There's a lot of literature out there. There's a lot of optimization literature out there, so this is merely intended to whet your appetites. What we're trying to do here is when we were sitting there with this data and project started before the Cable and Wireless acquisition. So the data in question applies to the project started with the Exodus network, and we were wondering how do we utilize the resources that we have best without the associated overhead with MPLS. Caveat, not an MPLS debate. This technique actually works with MPLS as well as without MPLS. Ben Amor, in fact, did a paper saying just basically that you can combine the two, if you so choose. Can it be done? Well, yes, it can be done, but most of the literature on it is very recent, so this is not something that we've got years and years of experience doing. We want to do this at the time we were in bankruptcy, so we want to minimize our cost structure for our network, and it makes the finance people incredibly happy, plus it's kind of cool. The caveat here with maximally is it's a kind of a thorny term. When you talk about using your network maximally, there's a concept of optimal general routing, which can be formulated in a number of different ways. But the idea there is, what is the maximum load I can put under optimal general routing? What is the maximum load I can put on my network if I can put each bit down any link I want? So you can fractionally divide things to your heart's content. Needless to say, our current protocols don't work that way. That was some of the rationale behind MPLS. With if I can define paths to possibly put my bits there. But as you all know, there's an associated scaling issues with that. Some of the literature goes through and says that optimum network flows can be represented as a set of positive link weights. The references there, more full references to these papers, are at the end of the presentation, if you guys want to look them up. Of course, this being mathematicians, positive link weights are not necessarily integer positive link weights. So, you can end up with fractional link weights and those sorts of things that can't apply directly. So with current IGPs, determining optimum is according to Forts and Thurup, is NP hard, but they managed to get using a local search technique to within 3% of optimum for the proposed AT&T WorldNet backbone. The paper is published in '99, so that backbone is probably actually in operation today. Okay, Josh is scoffing, so maybe not. As I said, the first one I ran across was that paper that was published in '99. There's a couple other papers I've looked at since then, published 2000, 2001. How easy it is to do this really depends tremendously upon what your network looks like. How many nodes do you have? How many arcs do you have? What are the size of your arcs? What do your flows look like? Where are they from? What are their sizes, etc.? In order to do any of this, though, what you need is to be able to get accurate flow data between your backbone nodes and some sort of optimization routine or routines to apply to the data in an attempt to iterate over it and improve the metric set. Let's go ahead and dive into how to get the data first, since we need that before we can play with the models. By the way, I apologize for the quotes instead of bullets. I did this on StarOffice, and apparently PowerPoint doesn't like StarOffice. Using NetFlow is the only way we've managed to figure out how to do this without using some sort of overlay model, the ATM or the MPLS overlay models that are very popular. We looked at a variety of products, including building our own, and ended up settling on the Ixia Camus product set because it offers some things, including inter-domain stuff that the other people in the panel are talking about. This kind of gets to what Josh was talking about in the question. Last time, vendor hardware-software combinations not always supported with NetFlow feature set. We've got a largely Cisco backbone, actually an all Cisco backbone, 3967, and the mixes and matches are all slightly different, so getting everything in balance is not always easy. Specifically with the combination with the iOS combination, we only have some of the backbone routers at this point that support gathering net flow for this tool because we don't have the right iOS on it, and ops foolishly will not let me deploy untested iOS on the router so I can gather data. So I'm waiting on that one. And the sampling rate for the data set that we gather does need to be grossed up. I'll get to in the slide. Based on the sampling rate we chose, it's 1 in 100. We're working with Josh et al. To they've got a promising technique to use SNMP counter data to actually match that to the flow data to get closer to real numbers for what we're playing with. Configuration. We configured it inbound on the interfaces to the backbone routers because what we're interested in optimizing here is our backbone links. We're not as interested in optimizing the access infrastructure, since that tends to be fairly even, and given our data center structure, cheap. If there are problems there, we can add extra gigi. It's not a terrible expense. We chose the 1 in 100 sampling rate. It seemed to do nicely and not drive up CPU on any of our line cards too terribly high much. I think all the line cards operate under about 30% CPU, so they do nicely. The collectors peer with the backbone routers as route reflected clients, and they gather, among other things, the BGP next hop information, which is what we're going to actually use to assemble our intra-domain flow set. There's a nice little picture for you. It's kind of abstracted because I ran out of slide space. The customer service routers, customers' data center routers, transit gigi switch fabric, and the backbone routers. The red dots represent where we're gathering the data. Yeah, sure, Bill.
On the diagram, what is within the building? On the diagram, what is within the building and what is across the local metro area?
Well, everything is in the building except for the links to the backbone. All the lines below the backbone router and down are gigabit Ethernet, and the lines going up toward the backbone are either OC48 or OC12. Sure. How do we process the collected data? So once we get this, the tool outputs something where you say BGP next hop, and then it gives us bits per second, total bits, packets per second, and total packets. What we're interested in for this purposes is our bits per second rate. So we chuck the rest of it. After we summarize the daily to assemble, rather than taking one interval, we try to munge it over time. And we aggregate it across all the interfaces and the routers with the site. Mostly we're doing this to develop the model, and as the model gets more detailed, we're going to get more detail with our data set too. There are some issues with the munging. Data is average, it's not peak. It shouldn't be a problem because peak and average, just by looking at the MRTG graphs, tend to follow about the same ratios. So long as the ratios are going to be consistent on the flow matrix, it should be okay, because because the metrics that are optimal for average should be optimal for average plus 50%. But we're working on getting the peak data actually out of the data set, because that data is there. We just need to extract it in order to actually compare the results and verify that assumption. As I said, it assumes that both backbone routers, if you go back to this thing, you can see every data center has 2 backbone routers. It assumes that they function as a single backbone router for the purposes of modeling. Again, once things get refined a little bit, we're going to break that out into 2 separate routers and model that. Okay, what we do once we have the aggregated daily summaries, which is actually a much smaller file, is we go ahead and post-process it with a script that goes through and basically takes all the BGP next hops and correlates that to a data center. So what we're interested in, again, here, since we're munging the flow data from data centers, we want to know how much goes from Santa Clara 5 to Sterling 1. So what we need to do is we need to just take that and combine the data for each of those BGP next hops. As I said, currently, what I mentioned to you earlier, we're not grossing that sampling rate up. We're working on that SNMP technique to do so. Here's an example data set from middle of May sometime. Again, this is 1 in 100. I don't even remember when. I think this is the daily average for that. And this is just from the Santa Clara 8 data center to a couple of the other data centers that we've got there. Again, approximate data. You can't sit there and go, well, actually, this had this many bits in our network at this point, because, again, even if you multiply it by 100, it doesn't quite work out precisely. So we've got, at this point, we've got our data set. We know what our flows look like, and we know what our network looks like. Actually, we better know what our network looks like. So we have our constituent elements to actually start plugging into the model and building the model set. There are a couple different thoughts on this. One is to do it in an offline way, one is to do it in an online way. We decided offline is really the way to go, simply because, well, for a couple of reasons. One, doing optimization dynamically is something that is going to impose a whole other set of requirements. You have to have a lot more trust in your tool set. There's a speed issue. There's a deployment issue. You obviously don't want to shuffle your metrics at a point where doing so is going to break things. You overload link while you're redoing your metrics. Plus, at this point, really, our target is getting maximal utilization of the network over fairly long, medium to long period trends. And if we were really to be running our network so hot that we have to optimize multiple times a day, we really need more bandwidth, and bandwidth is cheap enough at this point that even in this climate, we can get extra circuits out of finance. There are a couple of assumptions, as there are within sort of any modeling detail. I'm assuming for the data that I'm going to show you that the flow set data that I'll show you in a second grows linearly, because what I'm trying to do is I'm trying to maximize, demonstrate how much maximum flow we can put over the specific network. So I'm assuming Santa Clara 8 increases 50% and simultaneously so does Boston. It doesn't take ECMP into account except for ECMP over paths directly between two routers, in which case that's just modeled by grossing up the link size. For that purposes, if we have 248s, it becomes 5 gig link. Not to say you can't do that, just our current model does not do that. What I did is I took the 3967 network and I condensed it down. I chose only the domestic network, and I aggregated the various data centers in the region. So all the Santa Clara data centers break down into a single Silicon Valley node. And the various WAN circuits, again, I did multiple WAN circuits and made them single circuits. Again, this is the purpose of the example for this today, not necessarily for what we're actually doing with the network. We also took 10 demand sets, because, well, more than 10 demand sets don't fit on slides very well. But the findings still hold for when we take this and we scale it up to a larger amount of demand sets and a larger amount of nodes. Yes, again, caveat, example data. I don't want people coming to me going, well, your presentation said this. I'm like, well, yes, but. So here's our example network. Nationwide backbone looks probably pretty typical for a lot of your tier 1 ISPs. All the links are OC48, and another assumption is that we assume there are no nodal constraints. So routers are assumed to actually be able to do line rate, and with most of those links being OC48, that's not really a problem. So here are our base demand sets that we've gathered out of the tool, and after we finished going through and munging that data, we've got it's all really very evident there. The current metric set that we're running, that we have deployed on our backbone, is based on roughly based on tweaked round trip time. So the base for the data, you measure round trip time between the nodes, and over the course of time, the metrics have gotten tweaked a little bit as the need for particular specific traffic engineering has arisen. But they're roughly consistent with round trip time currently. If you look under the current loads, the network is nicely over-provisioned, so there's plenty of load. There's not a problem currently, but what we're going to look at is how much more load can we put on the network before any individual link exceeds 80%, to allow for a little, microburstability that doesn't count the data traffic, it doesn't count on the data collection, et cetera. 80% is kind of an arbitrary number. You can set this number to anything you want: 70%, 60%, 95%, 110%. Oh, okay. We're going to pause a second while they switch the tape. Right back up. Just to recap, we're going to go ahead and see how much we can put on the links without exceeding 80% utilization. For an OC48, that figures out to 1,990 megabits per second. We're going to try to keep all the links doing that. So when we linearly increase, this is our set of shortest paths under the current network metric for those demands. It all should be, fairly self-explanatory there. When we increase those network load linearly, you can see the base load on the left for the specific link. Again, the links are, for this purpose, defined as arcs. They're directional. So Atlanta to Dallas is different from Dallas to Atlanta, as would make sense since, OC48s are 2.5 gigabits each direction. If you look at the current loading, that's what we've got. So we've got basically 2 hot links, 3 hot links, and everything else is fairly lightly utilized. And we can take our current network set, if we scale that demand by 88%, we start running into problems. And that we run into that problems, that cross-country Sunnyvale to Washington, D.C. link when we hit 1,986 megabits per second. This is the abracadabra slide. Various people, pre-reviewers, have said either they like it or they hate it. So basically, I'm trying not to have this turn into too much. Again, get too much deep into some of the literature. There's some references at the end to point you guys in the right direction, simply because it would take too long. In this particular model run, what I've gone through is I've done some of the stuff in the Wang Wang and Zhang paper, except tried to make sure that those weights are integer. And going through, and this is an example of the output of the AMPLE modeling language. In order to model optimal general routing and to model some of this other stuff, you end up using, if you ever taken an operations research class, or they use this in economics as well as operations research. If you're familiar with concepts of linear programming or integer programming or nonlinear programming, you use these techniques in order to determine your optimum flows, or in order to determine if your search algorithm is generating more optimal flows than the last iteration of your search algorithm. As I said, we use AMPLE and with the CPLEX solver for that. The way that tool works basically is you define, you've got one text file that's a model, and that in that text file you go through, you define your, like a typical program, you define your parameters, you define your sets that you're going to iterate over. You define your objective. In this case, you want to minimize overall network load. You could minimize the maximum amount of length. You can play with the objective function in different ways to get the results to get it to produce the results you want. And it also contains a list of constraints, such as I don't want to exceed a certain threshold capacity on my links. And then you have the data file, and the data file consists of a couple arrays of data, which specifies what the network looks like, as well as what the demands are, what your demand set looks like. When we apply this model data, that paths change, so you can see that's what our new paths look like. They're a little shorter on average than the other ones in terms of hop count. And that's what our link loading looks like. So under the revised metric set, we're able to put 330% more traffic on our network than we have today, as opposed to 88%. Substantial improvement. You've also noticed the link utilization is much better utilized at this point. We don't have single bottleneck links. We've got a couple of links. Either under the current load, it evens things out much more evenly, as well as under the maximum load. Again, with linear scaling, it follows that the current load is more evenly balanced, then your maximum load is also going to come up to be more evenly balanced. Some of the utilizations are still very low because I threw in that Seattle to Miami flow, which not a lot goes directly from Seattle to Miami, as well as the more heavily loaded cities, Sunnyvale, New York, and Washington, D.C. That's basically the gist of what we went through and produced. There are a couple of papers there. This is not intended to be a synoptic list. This is merely representative of some things you can play with. I can give you summaries if you'd like. Some of the tools, unfortunately, the AMPLE link doesn't look like it showed up very well. That's www.ample.com, and the Opal CPLEX tool. But CPLEX is the solver, and then the AMPLE and Opal are the languages in which you represent the model. And I'd like to thank State for help with learning the programming language. Go for it, Bill.
Could you go back to the question, the slide that had the after results?
Yes.
It looks like you're spreading out a lot of that traffic across a lot more of the links there. And I wonder what the performance implications are, will the path length increase, the average path length across the network is in this case?
Well, if you look at the new paths, the average path length actually goes down slightly. And as far, are you saying in terms of round trip time, or in terms of latency, or?
Yeah, both.
All of the above? Your path length on this particular model actually decreases. by changing the model, you can actually tweak it to take into various things into account. You could define a constraint, for example. I haven't, but you could define a constraint that says that you would assign a round-trip time value to each link and say that combined round-trip time on eligible paths may not exceed X. So by playing with the model, if in this particular case it's not a problem because your path length actually goes down and your round-trip times either go slightly down or stay pretty much consistent. But if you wanted to, you could define an extra constraint that says take this into account.
It seems counterintuitive. You'd think that if you're forcing traffic along an alternative, perhaps more circuitous path in order to spread that load out, that the path length would necessarily increase and the latency would necessarily be worse.
It depends on your specific network. In this particular example, with the 10 demand sets and with the network the way it looks like, what kind of ends up happening is rather than bottlenecking on that cross-country link, the traffic set tends to go, you have half the traffic set in the network. The flow ends up being slightly asymmetric. You have half the traffic set going over that cross-country link, and then the other half going bouncing through Chicago, which when you actually get down to a fiber path length, it's pretty close to the same distance. So your RTT stays pretty similar. Again, it's going to depend on your individual network as to what implications that has. You could send something, through London and back theoretically, which is why at that point, if you started seeing results like that, you'd want to implement some sort of constraint function that prevents that from happening.
Just one last data point.
Sure.
I bring this up because there is one provider in the United States that has a path that will include about 30 routers to get from places around the United States to other places around the United States. And when confronted with a complaint by the customers that there are 30 hops on this path and the performance sucks, they started doing some VPN so it looked like there's only one hop. And it looks like they only had a single hop, and some set of those complaints went away. I just thought that was a rather amusing example.
Yeah, it is rather amusing because a lot of people don't realize that it takes a router microseconds to forward a packet, whereas it's really how many fiber miles you're going through that's going to increase your latency. Yeah, I've had customers who complain, it's too many hops, and you're like, but they're all in the same city.
That's an application problem, though. Traceroute's broken.
The traceroute's broken? Okay, there you go. So Josh will be fixing traceroute, so it'll just take out the internet piece in the middle. Or yeah, I mean, you get the same effect if you use an MPLS core and you turn off TTL decrement. So, yes.
Does this optimization analysis, does it look at a factor like volatility to link failure?
Good question. No, the next step for us is to sit there and model this under link failure. I haven't figured out how to do that yet. I'm working on it.
Is anyone else in the room using BGP Nextop data to optimize internal performance?
One hand in the back of the room.
Could you just explain briefly what you're doing?
Yahoo's using it for flow-based analysis to see where our traffic is going for targeting who we want to peer with, or who would be an optimal choice for if we have 3 transit providers to get to it, which way do we want to go. So.
Gotcha.
Anyone else? Any other questions?
All right, Joel.
How hard are the modeling languages? Like, not everyone's got a master's degree, and
In Japanese studies?
Yeah, right. How long? How long did it take you to go through all that and figure it all out?
Yeah, there were some very frustrated messages going back and forth among the presenters where I was sort of ranting at it. The literature tends, except for the fourth and third paper, which is actually, they actually applied it to real networks. So that's actually a great starting place if you want to look at this, because they've actually got a real case study. That's the first one there. Some of them tend to be very theoretical and very mathematical, and it took by the time I really started digging into it, it took about a month to sit there and go through and really figure out enough to get a working model together. That's why it boils down to him helping me out tremendously with things like the syntax. And I'm like, I'm trying to do this. I don't know how to specify this, because when you're going through and using linear programming, you're basically, you try to translate the algebraic syntax, like in the paper, for example, to something that actually the language understands. So you're trying to say, I want it to iterate over the following sets with the following exceptions, and the syntax you use for this language is going to be slightly different than the syntax you use for C or Perl or something.
So you can put up your sample amples online somewhere, so we can...
I somehow suspect Cable and Wireless would object to
the modeling?
Well, you can actually get, it's defined as a multi-commodity network flow problem. It's basically how you end up defining the problem. And if you go to the Opal website, in fact, the one down there, they've got some sample sets, including a sample of a multi-commodity network flow problem, so you can actually see how that's implemented in Opal and then make the appropriate adjustments for your own network and data set. And these tools are free up to 300 variables or 300 constants in the language, which gives you enough to start playing around with them and developing your models and get the stuff working and develop cost justification. Yes. There are also some free alternatives out there, but I actually stuck with these because this is what some of the authors of the papers use. So I wanted to make sure that I had a language that I knew I could represent what I was trying to model in.
How would you go about addressing the validity or the sort of the border parameter of the modeling engine? I mean, how do you know in the end the modeling engine is accurate?
You mean as far as what sort of metrics it produces?
Mm-hmm.
Oh, well, you define your sort of routing problem where you go through and you say, with this particular link set, how do things flow? So that's one model, and then you have another model where you actually go through and say, okay, I want you to optimize my link set, and you take your existing flow data set, you plug it through the first model where it says how should things flow, and then you can actually look in the links and go, yeah, it's about right. And then when you take the results from the second set, plug them into the first set, and have it use the first model which you validated against existing data to evaluate the results of the second model, which actually produces the link metrics. Did that make any sense?
I kind of lost.
In a reasonably large network, how many link weight changes would this result in, and how many, that would result in more LSTs, and if you do this frequently, you'd have increased instability because of that?
Yes, you're right, but this is not something we do frequently. This is something that we would probably do in the order of about any time it would be a significant change based on the flow data. In Cable and Wireless's experience, they do a similar optimization, but their optimization is not based on link weights, it's based on more circuit routing stuff. In their experience, it's about every 6 months that they actually make a change, and it's a reasonably minor change.
Though you would probably expect that the changes would go up as your link utilizations went up, as you had less room to fiddle with.
Well, yeah, but once you start getting to the point, that's why you set the threshold of something like 80%. Once your flows actually start looking like that, and you start going, well, guys, we're regularly putting, 80% utilization on a number of circuits. You really want to start getting more bandwidth at that point, and giving yourself some more overhead. Anything else? All right, cool. I think we're probably going to have a break next.
Yeah, we won't fit anything else in before the break. So let's just break now, and when we come back, we'll listen to Joe from MFN and Matt from Global Crossing talk about interdomain traffic engineering and using this stuff to solve people stealing from you and solve congestion management. So we'll see you in a few. Hey. Thank you.
Alrighty. Well, they say you're supposed to picture people your audience like they're in their underwear. I don't think the person that said that realized that I might be standing in front of network engineers. So. Let's see. My name's peer policing, peer policy policing with NetFlow is my topic. My name is Matt Meyer, and I'm a senior network engineer at Global Crossing's IP engineering team. I'm part of the traffic engineering group, which is under Denver Maddox. If you were at the previous NANOG, we put together the MPLS bot that manages the backbone RSVP values for our TE traffic engineering mesh, MPLS mesh. Today I'll be talking to you a little bit about what XE and Global Crossing have been doing with NetFlow at Global Crossing. But first, a little bit about Global Crossing's network. You can see, well, the blah, 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 blah.
That's very interesting.
Marketing spam. I should address, though, that we are going through the Chapter 11 process. I'm a network engineer, not a CEO, but the good news supposedly is that we have a completed network, and going through the reorg process has caused us to slash costs dramatically and made us leaner and meaner. From behind the lines, I'd say that morale is really good, and that we're actually seeing customers turned up every day, and that's very encouraging to me. Peer policy policing with NetFlow, some kind of sterile topic or title. I tried to come up with a few more witty subtitles. There was the non-confrontational counselor version here, and then our appeal to universal rights with, and then there's Grandpa's version. Bottom line, we're just trying to find out if people are sending traffic to us that they shouldn't be, our peers who shouldn't be transiting our network, defining the problem. But before we get to the problem, let's cover a little bit of the background of the network. Currently, we have numerous telecoms and internet space companies going into Chapter 11 or much worse, debt reorg or liquidation. That's causing punctuated mass customer moves. Specifically the Chapter 7s, I saw some news the other day, KPM Quest sent out a note saying, customers, you need to find somewhere else to go. That weekend we were receiving queries to see how fast we could get things up to some European customers. And I have a sip of water here. Sector-wide layoffs are driving home that capital expenditures and recurring costs must be slashed. We are already seeing dramatic peering shifts and consolidations due to customer moves, and even if you, and that's making. Sorry about this. Peering is becoming less flexible because of all of this. There's a consolidation of traffic. Some will resort to uncouth methods to mitigate congestion and sidestep potential costs of appropriate peering policies. With fewer players, there'll be larger peerings. And those peerings will inherit more flux and less flexibility to deal with it, because you won't be able to just go buy new interfaces. And even if you can, perhaps your opposing peer will not have the cash on hand to buy the new interfaces that are required. So, and some of the more liberal peering channels, like the NAPs, may dry up or become heavily utilized. Again, if only due to capital expenditure constraints. Again, these conditions become prime for uncouth congestion mitigation, customers dumping traffic on or peers dumping traffic on your network. addressing the problem. It's time to think like a bean counter. Why is that? Well, everyone else is, and your job might depend on it, which is always a good reason. Is your peering being abused? Do you know? I mean, could you know that you know that you know that your peering isn't being abused? If you are able to say that your peering is not being abused, then you're able to prevent or lower capex due to longer upgrade cycles, due to the fact that you're not becoming everyone's default for the internet traffic. End goal: we want to know that we're running a tight ship. And we want to be alerted when uninvited traffic enters the network. Measurement. Okay, it is not rocket science. There's not much to it. We're just doing 1 to 100 net flow sampling at our border routers. That's points of the network. And we currently set PRS type flow export. We'll be doing we're looking at, that actually might change. There's a note on that a little bit later. The equipment, we have one centrally located collector. It's Ixia powered, their super fumatic Ixia traffic product. That's Fu is in type Kung, not type bar. The collectors are handling approximately 20 selected routers, and also doing IDGB peering with those border routers. And the records are updated for the routing tables every 5 minutes. So the collector's actually performing double duty on multiple levels. Everyone always asks what kind of box we're running, so I actually didn't know. So someone provided this. It's a dual Pentium 3, 1 gig memory, multiple Ultra 160 SCSI drives, and it is running FreeBSD current release. Here's some of the data we've come up with, or an example of some data, a report that we put together for an unspecified time period. The fields are router interface, receive peer bytes, percentage of peer-to-peer traffic. Note that the percentages are in thousands of percent here, so there's trace amounts of traffic. You'll see arriving on the interface and going to other peers. This is traffic that's being forwarded to us from other peers, and it should be all going to our customers. We kind of expect that there to be trace amounts. It hasn't been proven to be, but it's presumed that this traffic has something to do with the granularity of the routing table, along with the matchup with the flow statistics. We can crank that down if we need to, but what we're really looking for is just a big red flag that people are forwarding traffic to us. Here we have an example of the flow data that's pre-processed. Actually, Ixia has processed it, but we dumb it down a bit to provide a delineation between peer-bound versus customer-bound traffic. For a given interface, we have arriving packet counts, bytes, etc., packets per second over the observed time period. This is the aforementioned case where the customer is dually homed and forwards us traffic. You'll see here, actually, I'm sorry, I skipped over it, I guess. Here, there's a source AS of 99 and also a source AS of 111. It's impossible on a non-multi-point interface here to be receiving traffic from two adjacent ASs on the same link. And in fact, what this is a what would we call it? Incontinuity between providers, one provider's forwarding policy and our forwarding policy to that provider. They're asymmetric, and obviously, so when we do a reverse, when we look up the source of the route or the adjacency of the route, the adjacent AS, it shows up. Basically, bottom line, we have to ignore that. Actually, I think Josh, yeah, that's your name. Josh explained that rather well. That information you need to be suspicious of that type of information. If you were wondering, the traffic is not corrected for sampling rate, but if you're really excited about it, you can move the decimal over 2 places. Okay, so how did we do it? The process was we extracted the data with Ixia tools. That provided us with 24-hour cumulative byte counts. Actually, we didn't have to collect all this data. The Ixia tool allows us to tabulate, to collect tabulated data, and the storage requirements are extremely low for that. So we just tabulated the tabulated data. And ignored the incorrectly reported net flow data according to routing policy, the source stuff, and associated instead. It was tempting to use source AS, but we ignored it and used interface IP address, which implies which ASN we're peering with. So. Here's a graphical representation of another peering router, its peering sessions. It's similar from the data from 2 slides ago, except that the 7 lower peers all seem to. I'm not sure if you can tell, but there's an extremely small amount of traffic that is not bound for internal destinations. Internal being customers or ASNs that are are customers in customer space. There is one peer which has a peer question mark up there, and that peer seemed to be forwarding us an interesting amount of traffic that was turning around and going back out to our peers. As it turns out, John Ofterheit. John, are you here? No. John Ofterheit, our peering coordinator, was able to settle this. It actually turned out we were selling services to this particular peer. So, false alarm. So where we look and why. First of all, our design is hierarchical. We have an edge network. I don't have a pretty picture, but we have an edge and a redundant core. All the edge boxes run dual links up to the redundant core, and then we have a WAN layer that the core routers have redundant links up to. It's fairly it's a fairly common topology nowadays. Our peers tend to be on dedicated peering routers, though there are occasions where we have customers on peering routers. And our peering is consistent, fairly consistent, and very rich. And as such, because of this hierarchy, we have to look here. We have to go to the border router to collect flow statistics. If it wasn't, if we collected further into the network, we wouldn't catch traffic that was being forwarded to us and turning around on the same border router. So it's a pretty logical place for us to collect flow statistics. There are big routers, Juniper, Cisco, GSR, and barely any 7500s anymore. And it's a natural aggregation point for traffic, so you don't have to add up a bunch of interfaces to generalize the information for an ASN. So, in our analysis, we found that the BGP import policy gets in the way of trusting source AS. Trace levels of false peer-to-peer traffic associated with was associated with most of the interfaces. And for our initial beta, we had no peers that have been found blatantly defaulting to us.
Matt, can you explain a little bit more about why you didn't want to trust source AS?
Well, basically the source AS is the routing. The source AS, excuse me, perhaps I shouldn't, let me say it's the adjacent AS. We're doing collection of pure AS type or pure AS type collection as opposed to origin AS collection type. And as such, if we were, the policy that is, the routing policy that is used to determine what the adjacent AS is of the incoming flow is local to that border router. Now, the ASN who's forwarded you the traffic might have a different policy, a different exit policy. Perhaps they're preferring your announcement of the route. They should be, and your customer has perhaps signaled that that particular route should not be preferred on your backbone. So you end up transiting that traffic on the behalf of your customer. And that would be okay. We actually haven't seen very much of that, and that's another possibility for transiting traffic. But when you're doing the fact that your peer and your routing policies are not necessarily congruent makes the source AS a bit suspicious, and since that traffic is coming off a peer interface, you know where that traffic is coming from.
Said a slightly different way, when the router exports a flow record, said a slightly different way, when the router does a route lookup to figure out the network and AS information, it's simply looking in the FIB to see what value has been placed in a certain part of memory. That's either going to be origin AS or peer AS, depending on what you configured it for. When you make it peer AS, all it's doing is saying for the route to destination IP address, what's the first AS in the path? For the route to the source IP address, what's the first AS in the path? What Matt's saying is that there are going to be times where your return path to the source IP address is not the same as your inbound path to the IP address. Therefore, when you forward back to the source, you don't always know for sure that you're taking the same neighbor back, right? It's up to your local route selection on the router, and so it can change sometimes. But as Matt rightly points out, if you're collecting on the inbound interface to your network, as long as it's not a shared media like a NAP, you know who's on the other edge of that link, so you can always correct that. Does that make sense?
Thanks, Josh. Oh, was that any other questions? Sure.
How do you approach those situations like a NAP where you how do you approach this in places like a NAP where you don't have that guaranteed if it came in this port, it's from this AS?
In actuality, it works at the NAP as well because you have an association with a prefix and
But how do you tell
BPI VCI pair.
How do you tell with a pair like that? So not over the regular Ethernet, you can't.
What's that?
Okay, I follow.
Okay. Right.
You would need sub-interfaces.
Right.
Right. Right. Any other questions? Okay, I'll continue then. So far, so good. For the moment, we don't have people. It doesn't appear we have people defaulting to us. If they are, they're working awful hard at it because we can't see it. We can move forward and easily complete a detection system, and we're feeling more confident about possible tighter peering ahead. What's next? Well, we expect to change the flow export style from pure AS to origin AS. Normally, this would not be possible, but Ixier's product allows us to look at the where we need to. We're going to use the adjacent interface, use the interface to imply the adjacent AS, and where we don't need to, it will allow us to, when asking other questions on the network, it will prevent us from having to flop router configurations back and forth. Also, I'm sorry, there's something. I guess another point is that the Ixier product can provide us with to and through information for every ASN along an AS path, and so we can generalize the information for a particular ASN at any point within an AS path. And I think that's actually something fairly specific to Ixia. I don't know if anyone else, who knows? So, alrighty. We're going to put this on cron, and in the long term, we're looking to distribute collection a bit. Having one collector is just not, we want redundancy. Well, I don't know about redundancy. It's impossible, I guess, with flow collection. What's that? Nothing's impossible, says Josh. We're going to distribute collection currently we have a central collector, and we probably have one in Europe and one in Asia and a couple in the U.S. or something to that effect. Build in some visualization because VPs like that kind of stuff, and so do Knox. So, and integrate, and that integration will probably involve RRD tool or something to that effect. I really haven't looked at it that much, but in retrospect, I've lost my place in my notes. There we go. For me, this is a good exercise in NetFlow 101. I've been networking for a while now, and for some reason I've let other people think about this kind of stuff. And so for me, it was a really good introduction to NetFlow. And the sampling capability to our assessment has been excellent. Certainly the gauntlet has been thrown down earlier today for people to do a more current study in NetFlow sampling to actual traffic transferred and the accuracy levels. But 1 to 100 seem to suit our needs. We have some restored confidence in NetFlow's reliability with our use of this particular collector with the AS0 problems absolved, and with someone to support our every whim. Thank you very much, and that's my presentation. Any questions?
All right. So you built you got up a big tool up and running to look for people breaking your agreements, and then you didn't find any. So you're going to keep running this tool. Wouldn't it be better maybe to use it as a spot policer to say, hey, the traffic on this link has suddenly gone up 50%. Let's go police this link real quick with just a spot view. I mean, if that's your primary use of this data, then it sounds like it's bloated for the fact that you didn't find anything.
Actually, I really need to expound on that. We like to be proactive. We like it to discover when it's happening, right when it's happening, so we can turn to the perpetrator. Or I had a slide in here at one time that suggested perhaps the routing policy was woefully awry, but inform them of the accident. We're collecting the data anyway, and if we're collecting the data, we can use it for a number of possibilities. This is just one application. So we've made a commitment to collect the data, running a cron job to check and see if people are abusing peering. That takes 30 seconds or maybe 3 minutes.
I think Matthew's point is that they're primarily collecting and analyzing data for traffic engineering purposes, and this was an interesting application that they put some of the data analysis to, one of many applications, but it's one that we asked them to report on to this group, because peering policing is something that is of interest to a number of providers.
I think it's my opinion, and it's only my opinion, but as backbones fail, as people go into liquidation, that people are going to get desperate, and if they try stuff, we're tightening our belts, and we need to find. We need to make sure that we're not paying for upgrading interfaces that have only been slightly. Let's say someone's only defaulting certain traffic to you, and they did it gradually. You wouldn't notice it in that case. And what we'd rather do is, just have something that throws up a red flag when it happens. So,
what tackles get to that point to do that?
I think it's important to remember that it's impossible in this sort of paradigm to only go after problems that are real, because you don't know if they're real or not until you've measured and analyzed them, right? I mean, Global Crossing had a real fear that this was happening on a pretty broad scale. It's a negative response is just as valid as a positive response to say, hey, we can stop worrying about this. This is no longer a big concern for us. We don't have to worry about integrating this currently into our network and into our priorities. Were it happening, they could take action to stop it. Finding out that it's not currently happening and that they'll know when it does start happening is another problem solved, right?
Yep.
And that rightly points out that we sort of pigeonholed him into talking about this, but and told him specifically that he was not allowed to tell everyone all of the great and wonderful things that Global Crossing does. But yeah, I mean, there's lots of stuff you can do. This was just the thing that he had to do.
They made me do it.
I might mention that this is to the chagrin of his wife. Matt just had a new son 2 days ago, and she allowed him to come to NANOG and give this presentation, despite the fact that
if she's out there watching it, she probably is. I'm unworthy. Gosh darn it! Oh, there was something I wanted to. The one thing I don't want from this presentation. Well, do what you will, but the thing you shouldn't walk away from this presentation saying to yourself is, well, gee whiz, it wasn't happening to Global Crossing, so it won't happen to us. You know, I bet you in the next year, you know, there's, we do a presentation here that says, we're checking, we're watching. We may scare people into not defaulting to us, but where do you think they're going to go? You know. Any other questions? All righty, I think I'll hand off to Joe here. Yeah. Dysfunction up there. What's going on? Which button is it?
There's only one.
How is it? How do you make it go? Oh, there it is. Okay, gotcha.
F5. Oh, wait.
There we go. Cool. Can everybody hear me okay? Okay. So the last case study we have is a fairly simple one. Nothing really complicated here at all. The idea is, well, start at the beginning. I work at MFN. The background is this. Our network peers has a peer in Europe, and we have several points at which we peer, private peering links. For various reasons, we're unable to provision the amount of peering capacity between our networks in the 3 points at which we peer that we would like. So we've got kind of marginal connectivity. If you add up all the traffic that we send to them, and you add up the total capacity on the circuits, then we've got headroom. But because it's split between circuits and the traffic's not always evenly distributed, we can get congestion on 1 or 2 circuits, which is not good. Normally the approach to solve these sort of things quickly is just to sort of turn up another few circuits or just increase in port sizes. But in this case, the peer has some infrastructural problems behind their peering routers, which means they can't accommodate more traffic in the particular places. We're waiting on them to do some upgrades, apparently, or something like that. So the task really is to try and mitigate what congestion we have. Try and make it as good as you possibly can, given that it's quite possibly going to be bad to some degree, whatever we do. So the problem we have, and this may be becoming more sort of characteristic of a lot of problems that people see with peers, is that there are a lot of broadband subscribers in this peer. And we host a lot of content, and a lot of that content happens to be quite bursty. So transient hotspots, as it says, and content hosted within our network can cause sudden spikes towards this particular peer network, which will completely knock out one peering link. Make it congested to the point where just nothing really works. So the natural reaction to this, if it continues for any length of time, is that our customers will decide, well, you better send the packet some other way then, because it's no good sending them through MFN because our content's not reaching our eyeballs. And of course, that's not a solution that we like, because if they don't send traffic to us, we don't get paid. So, you know, although that might actually fix the congestion, it doesn't actually make anybody smile. So, to start with, we talked about in Miami about some general principles for how to do this stuff. And the general idea was that trying to sort of produce a solution to solve the problem and then just go home and sort of have a nice beer and go to sleep and be happy that everything's fixed is never going to happen, because the traffic is dynamic and the problem changes the whole time. So we end up with this iterative approach where you basically measure things, you apply some small tweaks to the network, and then you measure again. And you keep cycling around that process, and hopefully you head towards a situation that's better than when you started. So the place to start looking at that is to say, what do we have right now? So in this little diagram here, these numbers are
approximate. You'll notice a bit further down the line that the exact details of the prefixes we're sending and the AS paths and things have all been nicely anonymized in the slides. Because our peering contracts say we can measure all this stuff for our own use, but they don't necessarily want us to go and announce it to the world. So in this sort of day one scenario we have here, we've got 3 links in Europe. They're all STM1. As I said, we can't make them STM4, STM16 or anything. And the one in Frankfurt is really busy, which is not good. So the idea was basically this, to say basically there are going to be some big consumers in the network in or beyond this peer that most of the traffic for these bursty periods is being sunk to. So if we can identify those characteristics of those destinations, whether it's AS paths or prefixes or something, then maybe we can apply some local policy to control the exit points that we use to send that traffic. So if we say we have sort of 4 or 5 major identifiable destinations of traffic, it would be nice to spread those amongst the available peering links. So instead of all pointing down one link, which might cause big burstiness and big congestion on one circuit, we'll try and spread them so we can try and make the circuits sort of equally congested and try and make the actual effective congestion on any one circuit a bit less. So the tools we used for this, there's been plenty of people have talked about the business of the IX traffic product from Ixia. We have that installed on a box in Virginia, and that's what we used. All the measurement we were doing was on boxes in Europe, but it didn't seem to cause us any problems. And we expected to have to do some sort of scripting nastiness afterwards to try and analyze the data anyway. And of course we wouldn't use Perl because nobody in their right mind would use Perl. So the actual routers in place, the routers on our side are GSRs. The box that we're detecting the traffic on is a way over-spec'd, but at the same time rather modest Pentium box. As it says there, the load average is very, very low the whole time. We don't have an awful lot of disk on it because we don't need an awful lot of disk on it. So the message here is that you don't need a particularly complicated or fast or capable box to record this stuff. You can pretty much use anything that you could use on a desktop. The other thing we have is we have something that provides functionally the same sort of data as MRTG does, looking at interface stats, because our ultimate objective here is to try and reduce congestion on interfaces. So obviously being able to measure interfaces is good. So Duck is something that one of our MFN engineers developed down in San Jose, and it's like MRTG, but it's kind of optimized to measure a large number of interfaces on the network very quickly. So it polls the whole network at 30-second intervals and sort of stores the same kind of data. So this is a real sort of down to basics. I mean, it's not a very complicated thing to do, so we're going into some detail about exactly what we did, just in case people haven't tried this and want to give it a go. So we have to turn flow switching on particular interfaces that we want to measure. So we identify the interfaces that might contribute traffic towards our peer, which hopefully in a hierarchical model is just a small number of backbone links. But for various reasons, maybe the topology has been compromised in some places by salespeople. And maybe we have routers that have peers, customers, and transit links all on the same box. So maybe the large, so on some routers, the number of interfaces you actually have to measure are quite large. It's messy, but it's the way it is, so we have to live with that. If you turn IP route cache flow sampled on an interface, it tends to make the router have a little spasm. So it's not good to do that during the day because people get upset. So that's a main window thing. We found that out after the first time we did it. So now we main window that thing. The script kiddie thing was kind of interesting. We had a router from another little measuring project that wasn't actually exporting any flow data at all. But we did have IP route cache flow sampled enabled on an interface, mainly because we'd never bothered to turn it off because it would require a main window. So we thought, well, why do main if we don't have to? It wasn't exporting anything. It was sending traffic quite happily. But what happened was a couple of denial of service attacks using a big sort of range of randomized source addresses ended up with sending us basically an awful lot of what looked like flows to the router. So the router had to suddenly start dealing with a large amount of flow data. And it was doing version 5 exports, so it wasn't trying to do too much summarization. But it seems that it's distributed on the GSR. So it seems that the RAM on the line card that's being used to populate these flow tables was being exercised heavily. And it seemed like in the code release we were using, it almost seemed like someone had made the architectural decision that, if we run out of space for flows, then we'll just borrow some from the Ceph table or something like that. So the basic result was that the router didn't seem to perform very well. In fact, it basically died. So just on those interfaces. So just to let you know that we thought it was worth mentioning anyway, we like to find this out, that leaving IP route cache flow sampled on in all places can be an issue, and it's well worth testing these things in the lab with a traffic generator or something and finding out what the results are for pathological flow sets, because it's much nicer to do in the lab than it is in the live network. So there's a standard sort of flow config there with randomized addresses and things, and we use 1 to 1,000 as our flow sampling interval because we're really not interested in accuracy of the absolute numbers we receive at all. All we want to identify is hopefully some fairly distinguishable traffic sinks within the remote networks. And we measured for a reasonably long time. We got about 12 days worth of data. So measuring 1 to 1,000 based on our previous experience, we expected to get the same sort of distribution or the same sort of sorted list as you would have done with a higher sampling interval, perhaps over a lower time. So we didn't record the raw flow data on our little FreeBSD box in Virginia. Which in IX traffic parlance is tanks. They call them tanks. You pour this flow data. So we collected buckets instead, which are matrices. So we configured we collected net-to-net and AS path matrices because we expected that a lot of the data was being sunk directly into this regional network because common knowledge told us that they had a lot of broadband subscribers. But we didn't know for sure. So I mean, they could have had a transit customer which was on a wholesale level. So we didn't know. It didn't really hurt to sort of collect the estimate. And the amount of disk space consumed by this was really not that much, 50 megabytes just for all the routers. So that's based on measuring about sort of maximum about 8, minimum 3 interfaces on 3 routers. So I don't know if you can see that or not. That's an output from one of the IX traffic tools that shows us the distribution of traffic to ASs over these peering links. Now all the AS numbers are randomized. But what it basically told us is we have an awful lot of traffic being sunk to one AS. In fact, that was the AS that we're peering with. So this confirmed our suspicion that the traffic's being sunk directly in the next AS. It's not sort of downstream of it. And again, those normalization based on the sampling of all. So we looked at the next network to try and identify maybe some weaknesses within the next network that will synchronize traffic. And we've got this kind of output. The columns in the right all those packets and this one is again they're reasonably meaningful. So I typed out through a few lines of walk and came up with this, and we found out that most of the traffic is being sunk to a single /12, which is not very convenient. We'd rather it was easier. It'd be nice if it was traffic was distributed across a bunch of different features, because then we can just weight them differently at different peering points, maybe sort of increase in meds here or decrease in meds there and spread the traffic that way. But we can't do that. It's all one prefix, and at the end of the day, we're the closest exit, so that's not particularly convenient for balancing the traffic. So that was kind of a problem. So the first thing we did was talk to the peer and ask if they can send us some longer prefixes. They could mark no export on them to make sure we don't conflict with their other sort of advertisement policy. And we asked them that a few times in a variety of languages, and. And in the end, it seemed like we weren't a big priority for them in this particular issue. They had other things going on that were more deserving of their time. And it's certainly not suggesting that they're in any way bad people. But it got us to thinking, because it's always nice to be able to do these things yourself rather than rely on other people to do you favors. So what we did, Dave Rand, no longer at MFN for quite a while, left this little legacy piece of Perl script floating around, which is still used on a regular basis. It's a BGP implementation written in Perl, which basically allows us to inject routes into the backbone to manually alter things to overcome short-term problems. You could use anything for this. You could use a spare router, you get a Cisco router or a Juniper router or something. You could use Zebra, something like that, anything at all. We happen to have this thing already in there for other reasons. So what I did is I took the /12 and I generated 15 extra /16s to fill up, all but one of the /16s component in that /12, and pointed the next hop addresses within the /12 that wasn't covered. So the end result was we suddenly had 16 prefixes that were all pointing the same way as the /12 was advertised. So this gives us a bit more granularity without the peer having to do anything. So they're all tagged no export. We don't send them to customers or anything like that. This is just used within our network. And in fact, it doesn't actually modify the forwarding policy at all because they're all going to the same place. But what this does, it gives us 16 prefixes in the RIB, which now we can classify traffic against. So there's the objective. The better granularity I talked about is the first point. We'll try and, once we've identified exactly where the hot points are within the /12, maybe we can then use some of those /16s to point them down different peering interfaces and try and fix things up that way. And obviously we're letting the peer know what we're doing just in case their NetOps guys notice some sort of phenomenon that might be caused by this. We couldn't think of a way that this would affect them at all. It seems to be exactly the same forwarding policies we have right now, but, you know, we'll let them know what's